In this problem, we're posed with the situation of having a propeller shaft, which is made of a ductile material having a yield strength of 36 KSI. As a result of the loading on the propeller shaft, we have the planar state of stress that's shown there in the figure. What we want to do is figure out what the factor of safety is as predicted by the maximum shear stress theory of failure, and in comparison, what's the factor of safety as predicted by the maximum distortional energy for the material. In order to do this, of course, we need to start out by calculating our principal stresses. These are based on sigma average and R. Sigma average is the average of sigma x and sigma y. There is a zero value for sigma y. There's minus 17 KSI for sigma x. So this is going to be minus 8.5 KSI for sigma average. R, which is the radius of Moore's circle for this problem, will be sigma x minus sigma y divided by 2 squared, plus the shear stress component tau xy squared as that. So we have minus 17 over 2 squared plus 8.5 squared. So the value of R that we get from here is 12.02 KSI. From these two, we know that the principal stresses of sigma 1 and sigma 2 are given by sigma average plus R. So sigma 1 is 3.52 KSI. The other principal stress of sigma 2 is sigma average minus R, and that number is minus 20.52 KSI. So from this we conclude that in the sigma 1, sigma 2 plane, it's in the fourth quadrant. Let me draw an expanded view of that. If I plot my usual x-axis, sigma 1 and sigma 2 axes like this, we recall that the maximum shear stress boundary is like this, going from sigma y to minus sigma y. We recall that the maximum distortional energy boundary is an ellipse given by this. And what we want to do is calculate what the load line is for our principal stresses. So for the load line, that's sigma 2 is equal to some slope times sigma 1. In this case, the slope is a minus 20.52 divided by 3.52 sigma 1. So that's a minus 5.829 sigma 1. So our load line is looking something like this. And of course, what we want to do, as in the past, we need to calculate what sigma 1 is corresponding to the shear stress boundary, which I'll call sigma 1s, and then the boundary intersection of the maximum distortional energy with the load line. I'll call that sigma 1d, because that's where the distortional energy curve will cross that. So for the maximum shear stress boundary, I know that that's given by sigma 2 in the fourth quadrant. And sigma 2 is equal to sigma 1 minus the yield strength. So where this curve intersects the load line, I equate 1 and 2. Equating 1 and 2 means that I make minus 0.5829 sigma 1 equal to sigma 1 minus sigma y. So sigma 1 at the boundary for the maximum shear stress, so I'll call that sigma 1s, is given by the yield strength divided by 6.829, and that was given to us, I think, as a 60 KSI. So sigma 1s is 8.786 KSI. So that's the value there for sigma 1s. The other theory, the ellipse, well, I guess before I move on to that, what I want to do really is calculate the factor of safety. So the factor of safety for the maximum shear stress case, that's the ratio of the sigma 1s we just found divided by the actual principal stress there of sigma 1. So that's 8.786 divided by the sigma 1 we calculated, 3.52. So the factor of safety is 2.5. The maximum distortional energy boundary, that boundary is given by sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared equal to the yield strength squared. And so if I find the intersection between the load line, and the MDE curve here for maximum distortional energy, I basically substitute the load line equation into there. So that gives me sigma 1 squared minus sigma 1. Sigma 2 was minus 5.829 sigma 1. And then minus 5.829 sigma 1 squared is equal to sigma y squared. So from this, I solve for my sigma 1 maximum distortional energy. So that becomes the yield strength, sigma y, divided by the square root of 1 plus 5.829 plus 5.829 squared. Again, sigma y, the yield strength for this material, was 60. So this becomes 9.39 KSI. So this is where the load line crosses the ellipse in order to find the factor of safety for this loading as determined by the maximum distortional energy theory. We take the sigma 1d, which we just found, divided by the actual principal stress there of sigma 1. And that factor of safety becomes 2.67. So as almost all the other problems we have done on failure analysis, we need to calculate the principal stresses first. And once we have those, we need to find out where, in what quadrant of the sigma 1, sigma 2 plane that our actual state exists. For the ductile case, which is what this is, we found out that it was in the fourth quadrant. We find out where the load line intersects 1, the shear stress boundary, and 2, where it intersects the maximum distortional energy boundary. We calculated our factors of safety based on those two calculations.